Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schula at the UMNL University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about low delay filter banks. So let's get started. Last time we saw that an mdct type filter bank leads to an algorithmic delay of z to the power of -1 in the lower sampling rate, hence a delay of one block over the analysis and also synthesis filter bank. Remember, z to the power of -1 came from making the inverse delay matrix d of z causal. In addition to this one block, we usually need to take into account the so-called blocking delay, which results from assembling our incoming samples into blocks of length n. We first have to wait for n-1 incoming samples on the analysis side, and at the arrival of the nth sample, the block is full, and we can send it immediately to further processing. Hence, the blocking delay is n-1 samples. Observe that we have no blocking delay on the synthesis side. This means that the total delay is both this blocking delay plus the delay resulting from our matrices. In the case of our mdct type filter bank, the total delay, or so-called system delay, is our blocking delay of n-1 samples plus one block delay from the polyphase matrices, and is given by here, the nd. So it's our blocking delay of n-1 plus one block delay from the polyphase matrices. So we also have the length of our filter, L equals to 2n, which results in the system delay to be the length of the filters -1. This relation holds in general for para-unitary filter banks. Observe that mathematically it only makes sense to define a delay over the entire analysis and synthesis filter bank, because here we have the exact same signal as the input signal, just delay. After only the analysis, we only have subband signals, which look differently and have a different sampling rate. Hence, here we cannot really define a delay. For para-unitary filter banks, the only possibility to reduce the system delay is to reduce the filter length. But this also degrades the filter characteristics. For instance, it would lead to reduced stop band attenuation. Often in applications like real-time audio communications, it is desirable to have a lower end-to-end delay, but also good filters with high stop band attenuation, such that we will still obtain a good coding or compression performance.